Hello, my name is Pura Patel and I'm a third-year medical student at NSU, Florida. This presentation is on transfer learning versus de novo training of convolutional neural networks for detection of acute lymphoblastic leukemia. Acute lymphoblastic leukemia, or ALL, is an aggressive hematologic malignancy that requires an early diagnosis for a good outcome. Current diagnostic modalities, including microscopy as well as flow cytometry, are both time-intensive and require trained staff and specialized resources that may not be available in all settings. Convolutional neural networks, or CNNs, with transfer learning technology is a potentially effective means to diagnose ALL in resource-poor settings. Transfer learning may reduce the time and resources needed for CNN training by reducing the computational demand required for the training process. To implement transfer learning, an efficient net CNN model was coded in the Python programming language in two separate modes. Firstly, as a tailor-made de novo model with no pre-training, and secondly, as a pre-trained model for the transfer learning application. The schematic of the model is shown in Figure A, and for transfer learning, the final three layers were left untrained and then trained on the specific ALL dataset. Both models were trained on the CNMC dataset, which contains over 10,000 ALL blood smears. Accuracies and learning curves were then compared between both the tailor-made model and the pre-trained model. The results indicated that both the tailor-made and the transfer learning model trained successfully on a single T400 GPU, or graphic processing unit. The transfer learning model achieved 86% accuracy on a test dataset, with a total training time of roughly 8 minutes, whereas the de novo model, designed from scratch, achieved 96% accuracy, but it required 31 minutes of training time. Therefore, the transfer learning model had 10% lower accuracy, but required one-third the training time compared to the de novo tailor-made model. Figure B in the right panel shows the learning curves for both the de novo model on the left and the transfer learning model on the right, demonstrating that the de novo model has greater accuracy, instability, and variability, as seen on the green curve, early in the training process, but ultimately reaches a higher accuracy than the transfer learning model. In conclusion, this study demonstrates that there is a trade-off between training efficiency and performance in CNN models for ALL detection. In particular, transfer learning is beneficial in low-resource settings, enabling rapid adaptation to various image acquisition devices and microscopy devices. Future studies could explore hybrid approaches, which could combine pre-trained ALL-specific models with transfer learning for fine-tuning to specific image acquisition or microscopy devices. That concludes the presentation. Thank you for listening.